Hi, this is Lance from LangChain. I'm going to be talking about using LangGraph to build diverse and sophisticated RAG flows. So just to set the stage, the basic RAG flow you can see here starts with a question, retrieval of relevant documents from an index, which are passed into the context window of an LLM for generation of an answer grounded in the retrieved documents. So that's kind of the basic outline. And we can see it's like a very linear path. In practice, though, you often encounter a few different types of questions, like when do we actually want to retrieve based upon the context of the question? Are the retrieved documents actually good or not? And if they're not good, should we discard them? And then how do we loop back and retry retrieval with, for example, an improved question? So these types of questions motivate an idea of active RAG, which is a process where an LLM actually decides when and where to retrieve based upon like existing retrievals or existing generations. Now, when you think about this, there's a few different levels of control that you have over an LLM in a RAG application. The base case, like we saw with our chain, is you just use an LLM to choose a single steps output. So for example, in traditional RAG, you feed it documents and it decides the generation. So it's just kind of one step. Now, a lot of RAG workflows will use the idea of routing. So like given a question, should I route it to a vector store or a GraphDB? And we have seen this quite a bit. Now, this newer idea that I want to introduce is how do we build more sophisticated logical flows in a RAG pipeline that you let the LLM choose between different steps, but specify all the transitions that are available. And this is known as we call a state machine. Now, there's a few different architectures that have emerged to build different types of RAG chains. And of course, chains are traditionally used just for like very basic RAG. But this notion of a state machine is a bit newer. And LangGraph, which we recently released, provides a really nice way to build state machines for RAG and for other things. And the general idea here is that you can lay out more diverse and complicated RAG flows and then implement them as graphs. And it kind of motivates this more broad idea of like flow engineering and thinking through the actual like workflow that you want and then implementing it. And we're going to actually do that right now. So I'm going to take a recent paper called CRAG, Corrective RAG, which is really a nice method for active RAG that incorporates a few different ideas. So first you retrieve documents and then you grade them. Now, if at least one document exceeds the threshold for relevance, you go to generation. You generate your answer. And it does this knowledge refinement stage after that, but let's not worry about that for right now. It's kind of not essential for understanding the basic flow here. So again, you do a grade for relevance for every document. If any is relevant, you generate. Now, if they're all ambiguous or incorrect based upon your grader, you retrieve from an external source. They use web search. And then they pass that as their context for answer generation. So it's a really neat workflow where you're doing retrieval just like with basic RAG, but then you're reasoning about the documents. If they're relevant, go ahead and at least one is relevant, go ahead and generate. If they're not, retrieve from an alternative source and then pack that into the context and generate your answer. So let's see how we would implement this as a state machine using LangGraph. We'll make a few simplifications. We're going to first decide if any documents are relevant. We'll go ahead and do the web search to supplement the output. So that's just like kind of one minor modification. We'll use tabulary search for web search. We use query writing to optimize the search to optimize the web search, but it follows a lot of the intuitions of the main paper. Small note here, we set the tabulate API key. And another small note, I've already set my LangSmith API key, which we'll see is useful a bit later for observing the resulting traces. Now, I'm going to index 3 blog posts that I like. I'm going to use ChromaDB. I'm going to use OpenAI embeddings. I'm going to run this right now. This will create a vector store for me from these 3 blog posts. And then what I'm going to do is define a state. Now, this is kind of the core object that's going to be passed around my graph that I'm going to modify. And right here is where I define it. And the key point to note right now is it's just a dictionary. And it's going to contain things that are relevant for RAG, like question, documents, generation. And we'll see how we update that in a little bit. But the first thing to note is we define our state, and this is what's going to be modified in every node of our graph. Now, here's really the crux of it. And this is the thing I want to zoom in on a little bit. So when you kind of move from just thinking about prompts to thinking about overall flows, it's like kind of a fun and interesting exercise. I kind of think about this as, it's been mentioned on Twitter a little bit, more like flow engineering. So let's think through what was actually done in the paper and what modifications to our state are going to happen in each stage. So we start with a question. You can see that on the far left. And this kind of state is represented as a dictionary like we have. We start with a question. We perform retrieval from our vector store, which we just created. That's going to give us documents. So that's one node. We made an adjustment to our state by adding documents. That's step one. Now we have a second node where we're going to grade the documents. And in this node, we might filter some out. So we are making a modification to state, which is why it's a node. So we're going to have a grader. Then we're going to have what we're going to call a conditional edge. So we saw we went from question to retrieval. Retrieval always goes to grading. And now we have a decision. If any document is irrelevant, we're going to go ahead and do web search to supplement. And if they're all relevant, we'll go to generation. It's a minor kind of logical decision that we're going to make. If any are not relevant, we'll transform the query and we'll do web search and we'll use that for generation. So that's really it. And that's how we can kind of think about our flow and how our states can be modified throughout this flow. Now, all we then need to do, and I kind of found spending 10 minutes thinking carefully through your flow engineering is really valuable because from here, it's really just implementation details. And it's pretty easy, as you'll see. So basically, I'm going to run this code block, but then we can walk through some of it. I won't show you everything, so it'll get a little bit boring. But really, all we're doing is we're finding functions for every node that take in the state and modify it in some way. That's all that's going on. So think about retrieval. We run retrieval, we take in state. Remember, it's a dict. We get our state dict like this. We extract one key question from our dict. We pass that to a retriever, we get documents, and we write back out state now with documents key added. That's all. Generate's going to be similar. We take in state. Now we have our question and documents. We pull in a prompt. We define an LLM. We do minor post-processing on documents. We set up a chain for retrieval, for generation, which is just going to be take our prompt, plumb that to an LLM, parse the output to a string, and we run it right here, invoking our documents and our question to get our answer. We write that back to state. That's it. And you can kind of follow here for every node, we just define a function that performs the state modification that we want to do on that node. Grading documents is going to be the same. In this case, I do a little thing extra here because I actually define a Pydantic data model for my grader so that the output of that particular grading chain is a binary yes or no. You can look at the code. I'll make sure it's all shared. And that just makes sure that our output is very deterministic so that we then can down here perform logical filtering. So what you can see here is we define this search value, no, and we iterate through our documents, we grade them. If any document is graded as not relevant, we flag this search thing to yes. That means we're going to perform web search. We then add that to our state dict at the end. So run web search. Now that value is true. That's it. And you can kind of see we go through some other nodes here. There's a web search node. Now here is where our one conditional edge we define right here. This is where we decide to generate or not based on that search key. So we again get our state. Let's extract the various values. So we have this search value now. If search is yes, we return the next node that we want to go to. So in this case, it'll be transform query, which will then go to web search. Else, we go to generate. So what we can see is we laid out our graph, which you can kind of see up here. And now we define functions for all those nodes, as well as the conditional edge. And now we scroll down. All we have to do is just lay that out here, again, as our flow. And this is kind of what you might think of as like kind of flow engineering, where you're just laying out the graph as you drew it, where we have set our entry point as retrieve. We're adding an edge between retrieve and grade documents. So we went retrieval, grade documents. We add our conditional edge. Depending on the grade, either transform the query, go to web search, or just go to generate. We create an edge between transform the query and web search, then web search to generate, and then we also have an edge generate to end. And that's our whole graph. That's it. So we can just run this. And now I'm going to ask a question. So let's just say, how does agent memory work, for example? Let's just try that. And what this is going to do is going to print out what's going on as we run through this graph. So first, we can see output from retrieve. This is going to be all of our documents that we retrieved. So that's fine. This is from our retriever. Then you can see that we're doing a relevance check across our documents. And this is kind of interesting, right? You can see we are grading them here. One is graded as not relevant. And okay, you can see the documents are now filtered because we removed the one that's not relevant. And because one is not relevant, we decide, okay, we're going to just transform the query and run web search. And you can see after query transformation, we rewrite the question slightly. We then run web search. And you can see from web search, it searched from some additional sources, which you can actually see here. It's appended as so here it is. So here it's a new document appended from web search, which is from memory knowledge requirements. So it basically looked up some AI architecture related memory web results. So that's fine. That's exactly what we want to do. And then we generate a response. So that's great. And this is just showing you everything in kind of gory detail. But I'm going to show you one other thing that's really nice about this. If I go to LangSmith, I have my API key set, so all my generations are just logged to LangSmith. And I can see my LangGraph run here. Now what's really cool is this shows me all of my nodes. So remember, we had retrieve, grade. We evaluated the grade. Because one was irrelevant, we then went ahead and transformed the query. We did a web search. We appended that to our context. You can see all those steps are laid out here. In fact, you can even look at every single grader and its output. I will move this up slightly. So you can see the different scores for grades. Okay, so this particular retrieval was graded as not relevant. So that's fine. That can happen in some cases. And because of that, we did a query transformation. So we modified the question slightly. How does the memory system and artificial agents function? So it's just a minor rephrasing of the question. We did this Tavoli web search. This is where it queried from this particular blog post from Medium. So it's like a sane web query. We can like sanity check it. And then what's neat is we can go to our generate step, look at OpenAI, and here's our full prompt. How does the memory system in artificial agents function? And then here's all of our documents. So this is the web search, as well as we still have the relevant chunks that were retrieved from our blog posts. And then here's our answer. So that's really it. You can see how really moving from the notion of just like, oh, I should go back to the original. Moving from, I will try to open this up a little bit. Yeah, I can see my face still. The transition from laying out simple chains to flows is a really interesting and helpful way of thinking about why graphs are really interesting, because you can encode more sophisticated logical reasoning workflows, but in a very like clean and well-engineered way where you can specify all the transitions that you actually want to have executed. And I actually find this way of thinking and building kind of logical like workflows really intuitive. We have a blog post coming out tomorrow that discusses both implementing self-RAG as well as CRAG for two different active RAG approaches using this idea of state machines and LangGraph. So I encourage you to play with it. I found it really intuitive to work with. I also found inspection of traces to be quite intuitive using LangGraph, because every node is enumerated pretty clearly for you, which is not always the case when you're using other types of more complex reasoning approaches, for example, like agents. So in any case, I hope this was helpful, and I definitely encourage you to check out kind of this notion of like flow engineering using LangGraph, and in the context of RAG, it can be really powerful, hopefully, as you've seen here. Thank you.